Hi guys, my name is Steve Sandler. I'm the Managing Director of PicoTest, and I'm happy to be talking to you today about measuring inductors with DC bias all the way up to 125 amps. Got a lot to cover, so let's get started. So the first question you might have is, why do we want to measure these inductors at all? There's a couple of good reasons. One is that as efficiencies are increasing in our DC to DC converters, the inductor losses have a more significant impact, as we want to make sure that we quantify those better. The inductor has a major influence on voltage ripple, and the noise budgets are getting smaller, and so another reason is to get a better handle on voltage ripple. A third reason is that there's a lot of counterfeit materials, and particularly in magnetic core materials, and so this is one way to weed out counterfeit materials. And finally, for our simulation models, we need really accurate inductor representations, and so we get the data in order to make our accurate models. DC to DC converters are continuing to shrink, and as they get smaller, we need smaller components, including the inductors. When we shrink the inductors, we also need to make sure that we understand the change in inductance as a function of DC current, because saturation will impact operating efficiencies, and it'll also impact ripple. So while we want the components to be smaller, we also need to quantify them better in order to make sure that we still have sufficient design margins. When inductors have too much bias current, they saturate, and when they do saturate, we get an exponential rising current at the end of our waveform. And while that doesn't have a lot of impact on the fundamental frequencies, we can see here that it has a much greater impact on high frequency EMI. And I placed markers here, the green line and the red line, just so you can see how it is that as the inductor saturates, its nonlinear performance has a greater impact at the higher frequency emissions than it does near the fundamental. And so we really need to understand that as well. We want to make sure that we don't come close to saturating the core because of the EMI impacts. We can get more accurate data, or at least better resolution data, using a frequency response analyzer to get data in the frequency domain. And today I'm going to show you two methods that we can use in the frequency domain. This one is called a three-port measurement. We set the bias current using a constant current power supply. So a DC bench supply feeds constant current into a modulator. Here we're using a J2121A line injector as our modulator. That has an isolated current probe, so we can measure the current that's modulating in the inductor, the actual AC current, and that gets connected to one input of the frequency response analyzer. And we also measure the voltage across the inductor, and that's connected to channel 2 of our frequency response analyzer. And so after performing a calibration using a 1 ohm resistor that's included with the modulator, the frequency response analyzer divides voltage over current, and of course that's impedance. The frequency response analyzer gives us lots more detail, and we can look at it in a lot of different ways. And so one thing I'm showing here is a measurement on the left side of the inductor Q, the quality factor of the inductor, as a function of operating current, and they're color coded. So you can see 1.2 amps in red and 2.2 amps is in blue, and 3.3 amps is in green. And now we can very clearly see the operating Q, but also we can see it in very clear frequency domain detail. So we can pay careful attention near the switching frequency and its harmonics. We can also look at the impedance magnitude if we want to see that in the frequency domain, or the frequency response analyzer can also directly display the inductance here as an inductor. And so in the lower right-hand corner, we can see that the inductor at 1.2 amps measures 1.24 microhenries at 100 kilohertz. It measures 1.13 microhenries at 2.2 amps, not too much of a drop. And at 3.2 amps, it's all the way down to 779 nanohenries. And now we have very high resolution data for the inductor at any frequency of interest. And this method has advantages and also disadvantages. One advantage is that we can measure at the operating switching frequency most of the time, which is a really great thing. And another advantage is that this same setup can be used to measure negative input impedance of DC to DC converters. So you kind of get two measurements out of the setup. Disadvantages: one is that it requires external modulation of the voltage source. Another one is that the frequency range is somewhat limited. Most frequency response analyzers don't go above 50 megahertz. You'd probably have a hard time with interconnects above about 10 megahertz. But for most of our applications, that's more than enough. Also, it requires a high current power supply and high current interconnect. So to measure an inductor at 20 amps, you have to have a 20 amp biased power supply. And lastly, it has a DC ground loop in the measurement. So for best results, you really want a differential probe or isolating common mode transformer in measuring the voltage across the inductor. And so here's an example using this 3-port FRA method, and you can see the line injector is connected. The isolated current monitor goes to channel 1 of the frequency response analyzer. The modulator output is connected directly across one port of the inductor through the SMA connector, and the other SMA connector connects to channel 2 to measure the voltage across the inductor. Because of the ground loop, remember, we'd really like to have a differential amplifier there, or an isolating amplifier, maybe something like our J2113 or J2102, if you want to get the best quality data. But now here you can see the impedance versus frequency data in the upper right-hand corner, and also direct measurements of inductance versus frequency in the lower right corner at both 1 amp and also at 6 amps. And you can see that the inductance is kind of frequency dependent. It's not really a flat line in this case, and that's one of the qualities that we might be interested in seeing when we compare inductors. Another frequency domain technique is called the 2-port shunt-through, and the device that we're measuring is mounted in shunt, just like it was with the other modulator. The VNA provides a 50 ohm source output that gets injected directly across the inductor that we're measuring, and then we measure the voltage across the inductor on channel 2, which is also 50 ohms. There is also a DC ground loop in this measurement, so we need to isolate that. Here we would recommend either the J2102A or better the J2113A. And if you're interested in more details of that ground loop, I provided 2 links here that show it. This measurement setup can measure down as low as tens of microohms and up as high as hundreds of ohms, so it works really well for measuring low value inductors. And the impedance transformation is built into the software, so the software converts this directly into impedance and inductance. Here's the setup for the DC biased high current measurement using the 2-port shunt-through measurement. So you can see the 2 ports of the Bodie 100 are connected to the DUT board. You can see that in the inset a little bit clearer, but there's a Standex inductor mounted, and you can see the 2 connectors that are mounted for the 2-port shunt-through. The bias source has a current amplification or current scaling, so it takes in current from a benchtop power supply, multiplies it by 24, and that's what we provide with bias. So here we're showing 124 amps, and that means that we're delivering just a little over 5 amps from our bench supply. And again, I have some measurements that show the inductor mount in green, and then the inductor at 2 different operating currents, 48 amps and 125 amps in red and blue. And you can see that the measurement of our inductor at 48 amps is a little bit lower than we expect. It's supposed to be 400 nanohenries. We're measuring only almost 20% below that, and I'll get into why that is next. Here we can see the measurement schematically, and so you'll see the J2131A bias source effectively looks like an inductor. And we connect a inductor printed circuit board mount that has the inductor to it. And so when we make this measurement, we're actually measuring 2 inductors in parallel. One that's the J2131A and one that's the device that we want to measure. So what we're measuring is this parallel equivalent. And since we are only interested in the inductor that we mounted to the printed circuit board, we need to de-embed that. And so you can see there's an equation there that shows the measurement multiplied by the mount divided by the mount minus the measurement. That'll de-embed it. And so we need 2 measurements, one of the J2131A by itself, which is easiest measured with the printed circuit board, just no inductor mounted. And then one, we need a measurement with the inductor mounted to the J2131. If we didn't correct this area, you can see the error curve. At 100 nanohenries, we'd be off by 8%. At 414 nanohenries, we'd be off by 24%. And at 5 microhenries, we'd be off by a whopping 79%. Using a math expression inside the Bode 100, we can actually do the de-embedding, and you can see there is the expression. So in this case, we took the 48 amp trace and multiplied it by the mount, or the measurement without the inductor included, and we divided that by the magnitude of the mount minus the 48 amp trace, and then we plotted that. Now you can see that we do get the right answer at about 420 nanohenries. I compared 4 data traces here. So I have data at 48 amps embedded and not de-embedded, and I have it at 125 amps de-embedded and also not de-embedded, partly because I wanted to show that that de-embedding equation was right. You can see that at 424 nanohenries, we're off by about 24%, and at 100 nanohenries, we're only off by about 8%. But we can also get rid of that inaccuracy using the math expression. Just to show how well this de-embedding works, we did measure a bunch of inductors, and so here I chose 3 samples, one that's down at 150 nanohenries, one that's up at 1.5 microhenries, and one at 5 microhenries. And we measured each of these 2 different ways, one using a 2-port shunt-through technique without connecting it to a bias source, so just the raw inductance measurement using a 2-port shunt-through measurement, and also using the J2131 DC bias source and the de-embedding equation. And I posted the errors there. So you can see that at 5 microhenries, the average difference was 2.2%. At 1.5 microhenries, 3.3%. At 150 nanohenries, 2.5%. You'll notice that the average error is independent of the inductance. So this is a systematic measurement offset, probably due to calibration. But we can accurately measure over the entire range, all the way up to maybe 5 or 10 microhenries without too much trouble, so long as we use that de-embedding function. And so this one also has advantages and disadvantages. One advantage is that we can measure at the operating switching frequency, and that can be quite high. I posted a link to an IEEE article I co-authored where we measured these inductors at hundreds of megahertz for embedded switchers. Using the de-embedding and calibration capabilities of vector network analyzers, it's a very accurate measurement, and it doesn't require an external modulator. Also, we can use 50 ohm source power amplifiers if we want to measure large AC sources for large signal data instead of small signal data. And because of the current multiplication of the J2131A, the DC bench supply we need is only about 5.5 amps to be able to bias an inductor up to 125 amps. There are 2 disadvantages. One is that you need the ground isolator, and you need that also for the 3-port measurement. And even if we did 2-port impedance measurement without bias, we would still need that ground isolator. And it also requires that we de-embed the J2131, so we need to add that de-embedding equation, which we can do right inside the Bode 100, so it's not really much of a problem. Here's a nice clean setup picture showing an inductor being biased at 99 amps. There's a BAMP12 source power amplifier connected, so we can use larger AC signals to modulate the AC signal, so it's a larger signal. And you can see the ground isolator there. That's the J2113 connected to port 2. And you can see that the power supply, the external bench supply, is operating at about 4.15 amps to get 99 amps of bias current. So this is a nice, relatively portable measurement that can go all the way up to 125 amps. So today I showed 2 simple methods for measuring frequency-dependent inductance that include DC bias. I showed the 3-port FRA measurement that works well up to 20 amps. I showed a 2-port shunt-through measurement using the J2131A DC bias source that works up to 125 amps. And of course, you could parallel J2131As if you need to go to even higher current. A few warnings. One is be careful about self-heating. Self-heating can impact the results because while you think you're measuring at room temperature, the inductor can get quite hot. So you might want to use fewer data points, higher receiver bandwidth measurements, or even automation to enable the power supply, do a single frequency measurement, and then disable the power supply and then repeat that so that you have a cooling off period in between them. One more warning is that it's possible to damage the VNA if the inductor breaks loose or becomes desoldered during testing, and so you want to be careful of that, and you also want to make sure that the inductor is soldered on the top of the mount board, not on the bottom, so it doesn't fall off if the solder does melt. Well, thank you so much for attending my session today. I really enjoyed it, and I hope you did as well. If you want to learn more about the products that I showed today, you can visit picotest.com or omicron-lab.com, and it provided some links for other information that you can get to after the session. Feel free to connect with me at LinkedIn or on my LinkedIn group, Power Integrity for Distributed Systems, and you can find most of my new articles posted at picotest.com/blog.